Last class we used something what is usually called kinetic model of gases to derive the dependence between the average speed of particles in the gas. The average speed, I may sometimes use also this notation, or sometimes I can just use this notation. Anyway, I always mean the average speed of the particles inside ideal gas. And we said that this is equal to 3RT divided by molar mass. The derivation takes some time and it's not very easy, but it's inside the book on the page 146. So if somebody didn't understand last class, you have to just read it by yourself and understand. So the kinetic model of gases assumes four things. Particles move at straight lines. Collisions of particles are timeless. It means that they don't take any time. Every particle has zero volume. Well, I better put it as zero like a real zero. Zero volume. Maybe the most important assumption is that movement of particles is completely random. And 5, maybe also very important, but of course not realistic at all. There is no interaction between particles. So we use this kinetic model of gases, this 5 assumption, to derive this formula. Well, as a result, this formula is not perfect because, in fact, every collision takes some time. Every particle has some volume. Well, this is probably true. Particles move at straight lines. Movement of particles is completely random. This is also almost true. But there are interactions between particles. So you see that this assumption and this assumption And these assumptions are not really true. But if you don't make them, the equations are too difficult. Good, now, so does it mean that at temperature T, every particle has the same speed? Probably not. This is average particles speed. So if not every particle has the same speed, what are the speed of particles? Let's just try to analyze the situation for... Before we discuss this, let us say what is the average speed of particles for different gases. For hydrogen, and we are going to refer to the temperature of 20 degrees. We are going to use the measurement meter per second. So if I have a box of hydrogen molecules and the hydrogens are flowing inside, what is the speed of every single hydrogen molecule when it travels on the line? You see, the shortest one is 1 meter per second. That's the speed of the one hydrogen molecule between collisions. And the fastest one is 200 meters per second. What is the speed of the wind during typhoon? I think it's 200 kilometers per hour, something like this. Maybe, yeah, 200 kilometers per hour. Let's try to calculate it. 200 kilometers per hour, it means 200 meters per 306 seconds. 1, 2, 1, 2, 1, 3.6. 200 by 3.6 is a bit larger than 50, maybe 60. 60 meters per second. So that's the speed of the wind during typhoon. Okay. Now the answer to this one is two kilometers per second. That's remarkable speed. That's quite large. Of course, light is much faster, but still, for me, this number is a big number. So you're not even close. It's around 10% you get the speed. Okay. Okay. If you go to other gases, H2, for example, NH3, we see that here is a mass in the denominator. If something is heavy, the speed will be smaller. And of course, NH3 is 7, 8 times more heavy than this one. So probably we are going to divide this, but this is the square root of this 8. So in fact, turns out that 655 meters per second. Ammonia. If we go to N2, we get 511 meters per second. This is the interesting part, because nitrogen is the main component of the air around us. It means that any moment something hits us with the 500 meters per second speed. And we don't really feel it. No, we feel it. That's a pressure, atmospheric pressure we get from the pressure. Okay, and you see that for O2, that speed would be very similar, 478. And the last one I have is CO. And for CO, it is 408 meters per second. Somebody may say, no, something is wrong here. What is the mass of nitrogen? Once again? 14, right? And N2 has a mass of 2 times 14, which is 28. CO, which is The same mass, the same temperature, the same R should be the same number. It's not. Why? Because of this wrong assumption. We have real gas. This is ideal gas equation. Okay? So you see that even if you derive some nice formula and you compare with the real results, you are getting some differences, even 20%. So the assumption that we make about the real gas and the ideal gas are pretty strong assumption. And the reason is that nitrogen doesn't have any dipole moment, and CO has dipole moment. It can get together, the dipole moments can interact. So there are many things why, for example, the collision of CO are probably taking longer time than collisions of N2. Okay, we can go further. This is one of the things that we wanted to discuss. So now, since we already know what is the more or less average value of speed for different gases, let's try to answer a different question. If you look at one single particle of a gas traveling, it's going, hitting another particle, changing direction, hitting, and then collision. So maybe that's the history of travel of a single particle of gas, because it's all the time colliding with other ones. It's never a straight line, but these are the segments of a straight line. So now, you have distance 1, then distance 2, then distance 3, distance 4, distance 5, distance 6, and so on, and so on, and so on. I'm asking the following question. What is the average distance that you define as distance 1 plus distance 2 plus distance n divided by n? It means, on average, how much one particle of gas travels before hitting the next particle? How much travels before hitting the next particle? Of course, we are going to measure this in, well, we should measure in the meters, but I probably give you some hint. We will rather measure this in centimeters than meters, as you can expect. This thing is called free path. And the question I'm asking you now, oh yes. The temperature is still 20 degrees. And we have here H2. So how far H2 can travel before hitting something else? Just not to mistaken you, I write the answer in the orange. And turns out that it is 1.1 times 10 to the minus 5th. So two answers are pretty close. I would say they are still minus 1, minus 2, minus 3, minus 4, minus 5. Should be here. They are still 20 times too small, but it's probably the smallest error. So it means that these paths for single hydrogen molecule really look like that. There are no straight lines. The particle is practically staying in one place and all the time bumping into other molecules, which is also interesting observation. Let's try to find these free paths for other molecules. This free path for N2 at the same conditions is 0.592 times 10 to minus 5 centimeter. The free path for O2 is 0.534. For CO, 0.89 times 10 to minus 5. So it looks like these distances are always very, very short. So even if you say that gas is empty with a very small number of molecules inside, if you come to the real distances for us, these are very small things. Maybe this emptiness is not so empty, because the particles are all the time hitting other particles. Okay, let's try to discuss this further. We already know that instead of this, we should think about this. Now, this molecule traveling here has one collision, second collision, third collision, fourth collision, 5 collisions, 6 collisions, 7 collisions, and so on and so on and so on. What I'm asking is, how many collisions per 1 second? And I call it number of collisions of H2. Let's check if this agrees with mine. My calculation says 1.6, then 10 to 10, which is kind of similar with this and this. But you more or less know how to calculate this number, right? Yeah, not very difficult. But that's quite number of collisions per second. It is how much? A lot. I want to have this money. So we can now ask different questions. And the question we can ask is, how much D is going to change at different pressures? And what we are going to take, we are going to take nitrogen at a temperature 300 Kelvin. So this is around what, 70 degrees? No, 30 degrees. No, 20 something. That is maybe room temperature in Taiwan. So now, if the pressure is 100 pascals, the pressure is 0.1 Pascal. And the pressure is, I have to count how many zeros. 1, 2, 3, 4 Pascal. We know that the room temperature, the room pressure is around 10,000 Pascal. And we know that in the 10,000 Pascal the path was the D was approximately 10 to minus 5 centimeters. Okay, now we are making the pressure much smaller, 100 times smaller. Turns out that the free path is getting much longer. It's already 0.01 centimeter. If you change the pressure again 1,000 times, the free path is becoming already 10 centimeter. This one, which is considered to be already pretty good vacuum, many people want to have such vacuum, the distance between two collisions is 10,000 centimeters. We're saying in other ones 100 meters. Okay, then another question. If this is Earth, and you start from the Earth and you go up to 100 kilometers, okay, the atmosphere probably finishes at 50 kilometers. So after 50 kilometers there is just cosmos, vacuum. Okay? So now, what is the 3 path for the N2 before hitting another N2? Or hitting something else, doesn't have to be N2. Okay, I write the answer again in orange. $100 kilometers. So the extreme answer is winning. Well, somebody may say it doesn't make sense because if the particle goes this direction, it cannot be 100 kilometers, but I mean this direction, average one. Okay, let's continue. So, there is a natural question to ask next one. If now we are analyzing the average speed, and from the ideal gas law, I write once again and once again and once again. The average speed is related to temperature in that way. There is also a question to ask what is the real speed of particles. We already know that the average is this, but imagine the following. This is the speed of particle, and this is the number of particles. So every particle I has some speed, and many of them has the same speed. So you can imagine the following curve. We know that the average is here. You can imagine the following curves. This one has the proper average, but this one has the proper average too. This one has the proper average too. And finally, this one has proper average too. So, in this situation, there is exactly the same number of particles having small speeds and big speeds, and finally they average to this speed. In this one, particles virtually have all of them the same speed. There are few of them that have different ones. In this case, the dispersion is very large. In this case, there is not so many particles having small speed, and quite many of them having large speeds. Turns out that there is a curve called Boltzmann distribution, which says, well, I give it in the differential form, but there are also other ways. Number of particles having speed I is equal, for some reason there is 4 pi here, is equal to the total number of particles multiplied by the mass of a single particle divided by 2 pi kt to the power 3 over 2 multiplied by the speed square multiplied by the exponents. I have to make some space, otherwise it will not look good. The curve looks, I mean, the equation looks terrible, But unfortunately, the equation has pretty sad history. Boltzmann was a very clever person, and after deriving this equation, he was very proud, saying that this is the number of particles depending on the speed. So the shape of the, in fact, this one looks almost like the yellow curve on the plot I did. He derived this equation, and it was correct equation because the experiments were showing this. But many people didn't believe in the theory of quanta, that he used the derivation on. So finally, he was a very unhappy person because nobody believed him, and he just shot himself. It was maybe one of the worst suicide, most famous suicide in the history of science. And the reason was not because his wife went away, not because his children did something wrong, but because nobody wanted to accept his science. So such thing happens. Anyway, we have this equation. So now there is maybe a good moment to apply this equation. We can just write down the following data. Again, we take nitrogen. Again, we take temperature 20 Celsius, which is around the room temperature. And now I'm asking the following question. Between 0 meter per second and 100 meter per second. We already know from the previous class that the average speed was for nitrogen 511 meter per second. Well, this one was, yes, at 20 degrees. So now we are going to ask how many particles have this speed. Then we are going to ask how many between 100 and 300. Then how many between 300 and 500, and 500 and 700, finally 700, 900, and more than 900. I shouldn't write infinity probably. I should write rather the speed of light here instead of infinity, but you know what I mean. So speaking in other words, I'm taking the yellow curve and I'm dividing it. Small speeds, larger speeds, pretty large speeds, again. Okay, I used orange twice. Let it be cross. We are almost finishing. That's the last thing for today. And the next one would be blue. That would be these. And you know what I mean. So I only write the numbers. Turns out that there is very little particles having very small speed, only 1%. It means that this area is only 1% of the total area of particles. Next one, for this speed, there is 25%. For this one, it's 42%. For this one, 24. For this one, 7. And for this one, 1% again. So we see the first thing that this curve is pretty much diluted, spread, that only 40% is around the average speed, but much more is around shorter and higher speeds. Okay, and that's probably the last thing for today.